Okay, so the assignment from Wednesday had this kind of thing. I don't remember which side, it doesn't really matter. But you had an equilateral triangle. And what kind of load was applied to this? External load? Going to the right? Going down? Just straight down? Okay. And it asks you to calculate stress tensors and stuff like that for each of these beams. What you have to recognize is that this is a truss. Who can give me a definition of a truss? We didn't in my statics class. We didn't emphasize it too much. Anyone who took statics, not from me, this was a more important distinction. So the definition of a truss is members connected by pin joints or ball and socket joints in 3D. And all loads are applied at the joints. That has the unfortunate effect for usefulness of making any kind of weight disallowed. You know, you can't use truss methods with the thing isn't a truss if you include the weights of the members. But if it meets these requirements, then every member is only in tension or compression. So it's in only tension or compression. And so that means that once you figure out what the tension is or the compression is in each one of those members, you can use the approach we talked about last time. You know, like if you have, so once you solve the truss, you'll have something like this. Let's see, in this case that would be in compression. You can figure out what that value is. I don't know what it is. Call it L for load. And then the axial stress is going to be, well, this is in compression, so negative L over the cross-sectional area, and the cross-sectional area is given. Okay. So you just have to solve this structure. And I could go back and review how to do that, but I don't think I'm going to, because I think it's helpful to go back and look at your notes. This isn't a very complicated structure. Any other questions about that?
So do like statics solving?
Yeah, so this is just a simple statics problem. And then once you're done with the statics problem, then you're just taking whatever that axial force is and calculating the stress from that.
It seems to me like that beam, the bottom one with the L,
Yeah.
L on it, should have, some axial forces.
Uh-huh.
Wait, it wouldn't?
It doesn't. And actually, that's
You know, it would have like a full force joint or something. Like,
yeah. Well, these are all pin joints. So that's the idea, and so each of those pin joints only applies a force vector to the member. And here's the thing about what this is so the reason that this is true is that each member is a two-force member. The only loads on it are a force at one pin and a force at the other pin. So think now about, okay, so what does that mean? Well, we have two forces here. Newton's second law says that those forces have to be equal and opposite if it's in equilibrium, right? If those forces aren't equal and opposite, then this thing is accelerating by Newton's second law. And now think about this possibility. So like, okay, what about a force going that way and a force going that way? What would happen to that member? It'd spin, so it can't be in equilibrium that way either. So there's only two possibilities. Tension, where those forces are equal and opposite going away from the ends, or compression, where they're equal and opposite pushing towards the middle. That's true of any two-force member. Okay. Any other questions about that? So yeah, if those were not pin joints, if this looks like it's a fixed joint or something, but it's not supposed to be. But if there was a fixed joint or any kind of other joint, then you wouldn't have that two-force member thing. You'd also have a couple produced by the joint, and then this wouldn't be true. All right. So now we're done talking about, that was a real short thing we've done for the last day or two on bodies that are under loading patterns that satisfy the requirements for a stress element. Okay, that the most useful case of that is when an element is in compression or tension. But now we're moving on to beams. So what's a beam? A tasty drink? Tasty weekend drink? It's not very tasty. Don't go near that stuff. A beam is a long, slender member, and this is a key part too. The definition of a beam involves the way that it's loaded. So it's a long, slender member undergoing non-axial loads, non-axial loading. It can be axial. There can also be axial loads, but there has to be some non-axial part. So there has to be couples or transverse forces or something like that. Axial forces are allowed too. The stresses that are developed in beams depend on 4 types of internal loads. Mm-hmm.
so if you have a beam that's, or a bar, I guess, it's like,
Bar.
well, if it's straight up and down,
Yeah, right.
it doesn't have non.
I was just thinking of the bear thing.
Like instead,
Right.
it's not considered
It's not. Yeah, it's considered a column. If it's under compression, they call it a column. Nobody makes too big a deal out of it. I don't know why they made distinctions. Anyone made distinctions like that in the first place. But if you just want to sound, if you just want to sound like smart to someone, you know. Yeah, exactly. Yeah, that's a column. Stresses and beams depend on 4 types of internal loads. Oh, by the way, speaking of beams, you know, the beams that they use in construction projects are like T-shaped or I-shaped. If you were using this object only to resist compressive or tensile loads, there'd be no reason to shape it like that. That's a lot of work for zero benefit. You might as well just make it a round shaft or whatever. But the reason it's shaped like that is because it's a beam. It's going to be used to resist transverse loads and couples. And that, for the given amount of material that they use in an I-beam, that's a really effective shape for resisting deformation and bending, deformation due to transverse forces. So it's shaped like that because it's used as a beam, not used as a column or a bar.
Well, it's called I-beam.
Yeah, right. Not an I-bar. Right.
Something that Apple would come up.
Yeah. Yeah, that's true. Okay, so the 4 types of internal loads that this depends on are tension, shear force, bending moment, and one that we didn't talk about in statics, torsion. And torsion is an internal moment about the long axis of the beam. Okay, like a twisting of the beam, wringing out the beam, you know. So we have to spend a little time talking about how to calculate these internal loads. So, okay, let's brief digression. How do we calculate these internal loads? So we're going to spend a couple days going back into internal loads. Okay, so let's set up a problem. Let's say that this beam it's a cantilever beam. It's a fixed joint with a wall. And there is a load at the end of 1,000 newtons at an angle of 45 degrees above the horizontal. I guess that's 45 degrees below the horizontal. And then a couple applied at the end. This is the torsion part that we didn't deal with in statics. Also applied at the end. And we want to know what are the internal loads at the center line. So what are the tension, shear force, actually, let me first start by talking about it a little more generally. So what are the internal loads at this dotted line? So let's say that this is 1/2 meter.
So we have max.
No, let's ignore that. And this is 1/2 meter. Okay, so what we're going to do is we know that the beam over here makes a fixed joint with the wall. Okay, so it resists any kind of translation and any kind of rotation. And we're going to, as our free body, instead of isolating the whole thing, which we're more used to, we're going to just isolate the half here that ends right where we want to find those internal loads. And then we're going to say that at that dotted line, our chosen object, the left half, makes a fixed joint with the part that we're not choosing. Okay. So we're going to isolate the left half. I always say not to do this in free body diagrams, but I'm going to just draw something here so you can see the part that we're skipping. Wait, I'm getting ahead of myself. I'm sorry. Don't isolate that yet. First, we have to calculate the external loads of the wall. Okay, so first we're going to isolate the whole beam. And calculate the external loads at the wall on the left. Okay, we're ignoring the weight. Over at the wall, we have a full force vector, if we're thinking in 2D. I'll call that R. Okay? And we have a couple keeping it from moving, rotating this way. Okay? And now we have a new couple in there that we haven't dealt with before to keep it from spinning due to that couple that we're applying at the end. So okay, I'll write it like, we have this, I'll call it MR, the reaction moment. And then we also have a reaction couple that I'll call fancy TR, like the reaction torque. And then we have those applied external loads on the right side. I'll write those in components. So that's going to be, what was that force, 1,000? Okay, so that's going to be negative 707.1, negative 707.1. And then our applied torque, 5,000. Okay, any questions about how I chose the reactions that I chose, why I chose? The thing that none of you have seen before is that reaction torsion. So, but remember this, in statics we had one or two problems where where it was fully three-dimensional motion. And in three-dimensional motion, a fixed joint like this applies 3 components of force and 3 components of couples to resist that motion. So we could write this as full 3 dimensions of a reaction force and a full 3 dimensions of a reaction couple. But the only ones that are going to be non-zero are the forces in the plane where these loads are applied, and the couples about about an axis coming out of the board, and one along the long axis of the beam. So all I did was single out the components of these loads that are going to be non-zero.
Can we combine
The torques, the couples? Yeah, sure.
what's the unit for that?
Those are Newton meters. They're moments.
Is that 5,000?
Yes.
Is this Newton?
Oh, Newton meters, I'm sorry. That's why you were asking. Okay, yeah. Thank you. This is Newtons. Okay, well, I'm going to write out the table. Pancake artist row 4, marzipan. I'm going to call this the origin. So at the left end, the coordinates are 0. Who in this class has never seen this table before? Oh, okay. Yeah. Well, let me say something about that. I should have done that first. This will be quick. You don't have to erase this if you don't want. I'll come back to it. Okay, so this is a table for organizing your values that go into Newton's second law and the moment equation, the rotational version of Newton's second law. The mnemonic device is pancake, artist, row, 4, marzipan. It's proprietary. Pancake artists. This is the clever one. Row is like, that's the Greek letter rho, but it's like the word row. 4, marzipan. And so what you do is you just go down, you make a row for each force or each load that you're dealing with. In the P column, you enter the coordinates of the point where the force is applied. Under A, you enter the coordinates of the about point. You have to keep the same about point for the whole rigid body. So one of these tables represents a whole rigid body. So that's the coordinates of the about point. Rho is then just P minus A. F is the force vector. And the moment then is just equal to rho cross F. So it's nothing new. It's exactly the exact way that everybody calculated moments in statics. It's just a way to organize it so you don't get your signs backwards and whatever, and you have everything in one place. So then you'll have a column for one force, a column for the next force, so on. And then when you get to Newton's second law, you have that the sum of the forces is equal to 0 in equilibrium. Well, those forces, you can just go right down this column and They're all listed here. And the rotational equation, whoops, Rn2L says the sum of the moments about A is equal to 0. And you can just get those right out of this column. So I like it. Okay, so what? I don't know. I have people send me Facebook requests like 5 years after they graduated from here or whatever, and they're like, I still use the Pancake Table. So I like it. I'm going to keep using it.
No, I mean, like in previous classes, you'd stop using it later on, like as we
No.
When we calculated internal loads, you didn't.
Oh, yeah. You're right. Yeah, I'm not going to use it always for internal loads. I always use it in dynamics and statics. Well, no, that was statics. Okay, anyways. I use it pretty often. Okay. So here's the table for the example we're doing. Pancake artists, row 4, marzipan. Yeah, the first time I taught statics at the U, people were getting confused about that, and I was like, oh, yeah, you calculate it all the same way, like this, and I just made that table, and the thing that took me longer to establish was the mnemonic device that I was going to settle on. I cycled through a few of those. Princeton athletes row for mommy was one. I don't know, there were a couple. But they all have to have row in the middle, you know. I didn't get into Princeton, so it was probably my bitterness speaking. Okay.
Really, we didn't either.
Not yet. Okay, so what are we doing up here? So we're just going to go through all of these loads. Couples, by the way, we don't care about where those are just like a pure moment, so we don't care where those are applied. So all we do with couples is just enter them in the last column. So, okay, let's first do those loads at the end. We'll call that the origin. And I'm going to make the about point there also. There's no reason you have to do that, but once you choose it for, it's a single rigid body, so once you choose an about point for one load, you have to keep it for the entire rigid body. So 0 minus 0 gives a row vector of 0. The force vector, so let's make this Rx, Ry. And now the cross product is just 0 times Ry minus 0 times Rx, so 0. That's really a Z component, I mean. Actually, we better, now that I think about it, we better keep all these components. We better do it 3D, because we're going to have that X component due to the torsion. But you know better. Okay, I'll change it. Okay, so 0, 0, 0 is the moment produced by R. And then we have the couple MR. That's about the Z-axis. And then we have the couple TR, that's about the x-axis. So that's all the loads on the left end of the beam. And now we'll go to these two. The coordinates of the right end are 1, 0, 0. The about point is still 0. So subtract and you get 1, 0, 0. The force vector was negative 707.1, negative 707.10. And so the cross product is negative, so 0, 0, negative 707.1. And then the last load is a couple in the x direction. Is that positive or negative? That 5,000 Newton meter couple? Yep, because it follows the right-hand rule. And so if this is the x-axis, I guess I'll draw out the coordinate system. So I'm thinking of this coordinate system. Your thumb's in the direction of that vector, and you represent a couple vector with that double arrow like that. And so yeah, that's positive. And so we have 5,000, 0, 0. So now Newton's second law says Rx, Ry, 0 plus negative 707.1, negative 707.10 is equal to zeros. So Rx, Ry is equal to positive 707.1, positive 707.10. And then the moment equation says 0, 0, mr plus tr 0, 0. Question? Plus 0, 0, negative 707.1 plus 5,000, 0, 0 is equal to zeros. And so you get that TR is equal to negative 5,000, bless you, and MR is equal to positive 707.1. Any questions so far? Are we done? No, that wasn't the question. Okay, so we just needed those external loads so that we could make that cut in the middle and calculate the internal loads at that dotted line. Okay, so now, yeah.
The 5,000 meter, how do you decide, like, you put your thumb in there, you have your fingers, but how do you know that's positive? I mean,
Actually, that's funny. That the right-hand rule that I did really didn't.
oh, it's just 5,000.
It's just because it's in the direction of the x direction. That's why there was no reason to do the right-hand rule there. I just wanted to show my muscles.
That would be the kind of, if it was.
Yeah, if you would use your right-hand rule if you wanted to think about what direction of rotation that meant. Then you put your thumb in the direction of the axis, and that means a a rotation that way. What?
I just realized I'm the only girl here.
What? That's ridiculous. Where's Sophia?
She decided not to take the class for a default.
We'll get to the bottom of this. Okay. Okay. So now we're going to isolate the left half of the beam. And this is the one that I drew this before. So there's all this part of the beam that we're ignoring. And now what we know is we have, on the left end, we have a couple MR of positive 707.1. We have a couple in the negative x direction of 5,000. I'm going to write that this way. This computer doesn't like when I write close to the edges. Okay, and then we had a force vector of positive 707.1, positive 707.1. And now the interface between the ghost part and the part that we're isolating, that's a fixed joint. And so the loads that are applied by the missing part to the part that we're isolating are a force vector. Let's see. I'll call that F. And a couple, internal couple. I'll call all of these sub I, so for internal. So internal force, internal couple, and then an internal couple about the x-axis, TI. What? I am, yeah. I'm getting there, yes. But for now, I'm just doing these in the axis directions. I'm just trying to emphasize that all we're doing is treating as a fixed joint. Okay, we're gonna eventually do everything with that sort of wacky internal load sign convention, but all that's doing is treating it as a fixed joint. So now, I'm not going to write out the table this time. I'm just going to go straight to Newton's second law and the rotational equation. So the forces that we have are the positive 707.1, positive 707.1, and then 0. I'll just, since we're not going to have any forces in the z direction, or in the z direction, I'm going to leave that off. Do I really want to do this? I want to, let's do the table. I know, I'm sorry about that. What if I was like sponsored by an eraser company? They like gave me like kickbacks to like erase stuff all the time. Yeah, right, exactly.
I'd say you get one.
Okay, so we'll call this the origin and the about point again. So at the origin, the row vector is 0. The force vector is 707.1, 707.10, and there's no moment. And then we can lump these two together. These are just two components of a couple. We have 5,000 Newton meters in the negative x direction and 707.1 in the positive z direction. What did I say, negative 5,000? And then 0, and then positive 707.1. And now at the cut, that location is 0.500. The about point is still the origin. The row vector is 0.500. And the first thing we have is that force, Fi. And the cross product is 0, 0, positive 0.5 Fi y. And then the last thing we have is the combination of the couple Ti and the couple Mi. Those are both in the positive direction, so we have Ti in the x direction, Mi in the z direction. So Newton's second law says 707.1, 707.1 plus Fix Fiy is equal to zeros. And the moment equation says negative 5,000, 0, positive 707.1, plus 0, 0, 0.5 Fiy, plus Ti, 0, Mi, is equal to zeros. I wrote out the y equation here, but that's just 0 equals 0. And if we solve this, we get Fi is equal to negative 707.1, negative 707.1. And Mi is equal to negative 353.5, I think, right? And Ti is equal to positive 5,000. Any questions about that? Well, I'm not going to go through the calculation, but if we had chosen arbitrarily to work from the other side, if we'd chosen to isolate the right side and calculate the force, the internal loads that the left side applies to the right side, we would have gotten the same values but opposite signs. Okay? So that way of thinking about it is a little confusing. So we're going to choose a new sign convention. Let me write that down. So if we had worked from right to left, we would have gotten equal and opposite values. Can anyone give a one-law explanation for why that is? Yeah, right. Newton's third law is the reason. Because instead of calculating the loads applied to the left by the right, we'd be calculating the loads applied to the right by the left. And it has to be equal and opposite. So we're going to introduce a new sign convention. That doesn't have that problem. So if you're looking from the left and you're looking at loads on the right side, that's a positive tension. That's a positive shear force. That's a positive bending moment. And the torsion I'll make with a fancy T. Okay? So these are all the positive values working left to right. What was what? Shear force. And then if you're working right to left, it's all the opposite values. So a positive tension goes this way. A positive shear force goes this way. A positive bending moment goes this way. And a positive torsion goes that way. And so if you use those sign conventions, then if you do this problem working from the left, you get whatever values. Then you throw that aside, work from the right, and you get the exact same values. You don't have to worry about that Newton's third law thing. And I can't help you remember most of these, but it's easy to remember the sign convention for the bending moment about the z-axis. So for that internal M, a moment that makes a beam do this is positive. And a moment that makes a beam do this is negative. So you should never forget that one at least. Okay, any questions? Okay, we'll keep going with this next time. Next time you see me, I'll be 43. Today I'm 42. Which means, thank you. That's right, you understood. Yeah, right.